Hello again, welcome to Magnetic Fields number 12, Moving Charges in Magnetic Fields. So what we're going to do here, when we've been doing a conductor in a magnetic field, I did mention that it's because of the electrons that are flowing, that represents the current, that it experiences a force. So if we simplify that down and make it just an individual charge, we can see that that individual charge, if it's moving through a magnetic field, it experiences a force. And for a moving charge, it experiences a force that's perpendicular to the velocity. And it's always perpendicular to the velocity. Now, the size of the force depends on a number of things. And it depends on the size of the charge, depends on the velocity of the charge, and the strength of the magnetic field. So those three things come into play. And we have this equation here, which is force due to the magnetic field. Q is equal, let's just bring it up, force is in newtons. Q is the charge of the particle, so we've used Q before. V is the velocity, meters per second. B is the magnetic field strength, and this is the angle at which it cuts, and for us it's always going to be 90 degrees, which means that's sine 90, which equals 1. So we pretty much ignore it, but it's there in existence because the real world is much more complicated than we make it out to be. Now, you need to be able to work out the direction of that force because it varies depending on if the charge is positive or negative, you see. And so you need to make use of what's called the right-hand motor rule for charged particles in brackets. And it's a little bit different. And the way I like to remember it is it's exactly the same as the right-hand rule, where your thumb was current, but remember that was conventional current, and if conventional current was being carried by a charge, it would be a positive charge. And so for working out the direction of force for a charged particle, your thumb represents positive charges, and then if you had a little wart here, or a little sixth finger growing out there, that would be negative charges. And so you just have to remember that. That's one way. Students have their own ways of remembering. Again, it's got to be the right hand. And so you still have the force coming out of the palm, and you still have the magnetic field represented by the fingers. So it's not too hard to apply. And so here's an example. Here's a radioactive source producing some charged particles. They come out a little opening and then find themselves in a uniform magnetic field. And if we used our right-hand rule, these are, what are they? Alpha particles, gamma particles, and beta particles. So we have positive, no charge. So the no charge particles just go straight through, experience no force. But the positive and the negative charges experience a force in opposite directions, and the curvature of this relates to their velocity and their mass and the amount of charge that they have in them. But just to verify it, you should be able to use your right hand rule to verify that I'm looking at the screen now. You should be similarly should be representing, the thumb would represent the alpha particle, the magnetic field's into the screen, so it goes like that. And the beta particle goes like that because I've got a little growth coming out here. So a bit of practice, get your head around that. Now, what happens is that because the force is always perpendicular to the velocity, the particles will undergo or go into circular motion. So it's always a perfect circle that they're moving in, because this is also happening in a vacuum in all the cases that we'll look at. Okay, and so here a positive charge will move in a anti-clockwise circle, and a negative charge will move in a clockwise circle. So just make sure you can verify that and you can recognize that. And again, another diagram just showing that the force is always perpendicular, and therefore it's going to be circular motion, and it's going to be a circle with a radius. And again, another diagram. So here, electrons are coming in. They go on a straight path until they hit the magnetic field. Then they're curved, and that curvature may result in them exiting the magnetic field at a certain point, and it will have a radius of curvature. Now this is very different from the motion that we got in charged particles in electric fields, isn't it? Because with electric fields they were moving in a parabola because they were accelerating in the direction of the electric field. So this is quite different, and therefore we can do some different things to it. Remembering this formula here, we've got that, got that, got that, got that, so we can use that. Now because it's moving in a circular path, we can also combine it to and recognize that the force being provided by the magnetic field is a centripetal force, and centripetal force is given by mass times velocity squared on r, and so we can combine these two sections here and cancel out two of the v's and bring it together, and we can work out the radius of that circle if we know the mass of the particle, the velocity, the charge, and the strength of the magnetic field. There's also a sign there, but again we pretty much ignore it. So that's the radius in meters. Kilograms is our standard units. If you're doing chemistry, watch out because you'll start using grams a lot. Physics, we use kilograms. Velocity, meters per second, coulombs, and teslas. So let's do a quick example. This diagram here, which we talked about before, the particles come in, we're given a mass of the protons, we're given the strength of the magnetic field, we're given the velocity, and typically we'd be asked to find out the other things that we could work out about it, and that would be the force and the radius. And that's supposed to be a little times by, and that's supposed to be the power. The charge of a proton is the same charge as an electron, 1.6 times by 10 to the minus 19 coulombs, but being positive. Notice, and they put the numbers in, I would probably like you to, ideally I would have liked them to have put all this into brackets so that if you're marking it, the examiners are marking it, they can see exactly what you've done. And make sure that you're using your EXP button on your calculator, and you should probably have your calculator in scientific mode because you're going to deal with very large or very small numbers. And you get, notice, let's get rid of that writing, that's just a little gentle reminder to do the right thing. And so you get a force, and then you need to know what that force is, and in this case it's upward. Now, but where are they relative to? Relative to that diagram, I think. Now the second part, so if you can give a direction, you do. And the radius formula again should have all this in brackets and should have a couple more lines of working. The line of working that's missing is probably what you do is you do that multiplication there, and you put that there, and then you do that multiplication there, and you put those two values so that you can make sure that you can go back and check your answers. Okay, and don't mind if you give your answer in scientific mode, that's okay as well. So you should now be able to do question 19 from the booklet. And the next video we're going to actually combine our understanding of magnetic and electric fields, and we're going to go back and have another look at mass spectrometers in a bit more detail. So that should be enough for today. Cheerio!